Hello ladies and gentlemen. Now this video is for period 2. They wanted me to take a look at the example with that poor fool Milton bobbing up and down in a wave pool. So let's talk about what's happening to Milton. He's going from a trough to a crest. So here's Milton down at the trough. Here's Milton up at the crest. We know a few things. We know that the bottom of the pool is here somewhere. And we know that when he's at the trough, he is 1.5 meters from the bottom of the pool. And we know that when he's at the crest, I believe he is 2.1 if I'm remembering correctly. 2.1 meters from the bottom of the pool. And you know that the time that it takes him to go from the trough to a crest was actually 1.25 seconds. So that's what we've got. And the question is, come up with an equation for good old Milton. Well, one of the things I think that we should realize is that if you're in a wave pool and if you're looking at it horizontally like I am here, what's happening is you have your waves, they go up, they go down, they go up, they go down, they go up, they go down, and that's what's happening. And Milton's actually just riding that wave. He's going from bottom to the top, from bottom to top, going up and down, up and down. He's actually not moving horizontally. He's just going up and down. We're going to want to model this using a trig function. So we have a choice. They didn't say which trig function we had to model this by. So we can either model it using sine or cosine. And in fact, in the course of this video, I'll do both. What we want to do is calculate the mean position curve. And that means finding out an equation for Milton that looks like this. A sine k theta or A cosine k theta, where we're going to want to take into account the amplitude and we're going to want to take into account the period. Once we figured this out, once we have the mean position curve, then we can include a vertical shift and a phase shift to match our curve to the given information. Okay, so let's start off with what we got. And again, I'm going to go after the mean position curve. And I think I'll use sine just to start off, okay? So I'm going to start with sine. So the first thing I want is my amplitude. Amplitude is going to equal my max minus my min divided by 2. So it's 2.1 minus 1.5 divided by 2, 0.3 meters. Which means, if we remember what amplitude means, it means that there's a horizontal cutting through this curve. Okay? It's cutting through it so that the amplitude goes up 0.3 meters to its maximum and it goes down 0.3 meters to its minimum. And for that to be the case, that horizontal has been moved up from where it normally is at the horizontal axis. It's been moved up 1.8 meters, which means that you are eventually going to have a vertical shift of 1.8 meters up. And we're going to hold on to that to later. I'm not going to use that right now, but we're definitely going to talk about that. So if this is 1.8, if I go up 0.3, I go to 2.1, which was my maximum. If I go down 0.3, I go to 1.5, which was my minimum. So everything's working out great. I know my amplitude, it's 0.3. Next is to get my period. Well, the period, this is half a wavelength. If we think about the sine curve, what a normal sine curve looks like is this. There's a top and a bottom, sorry. So our normal sine curve would look something like, starting here, going to here, going to here, going down to here, going to here. So there's my normal sine curve. The normal period for a sine curve is 360 degrees. So to go from a trough to a crest, now I don't have a trough and crest easily seen here, so let's go this way. Go from a trough to a crest, that's only half a wavelength. Okay? So the entire period will be 2 times the 1.25 seconds. So that's going to be 2.5 seconds, which will give you 1 complete wavelength. Okay? Now, what does that mean for the K value? Well, we know that period equals 360 divided by K. That K value is what works on the 360 to give us the period for each individual function. So in this case, we know that our period is 2.5. 360 divided by K. That's hard to do. We'll put it over top of 1. We'll cross multiply. 2.5 times K equals 360 times 1. Divide both sides by 2.5. We get K equals 360 divided by 2.5, which was 144. That is the numerical value that we need to put in here so that our period will be 2.5 seconds. So we've calculated our A and we've calculated our K. Okay? Let's put that into our equation. So what we know is we're going to have y equals 0.3 sine 144 t. Now I'm using t instead of theta because it's in terms of time. Our question is in terms of time, not really in terms of theta. Okay, well that's my mean position curve. If I was to graph this curve, this is what I'd get. Let's make it a little bit bigger so that I can do a little bit more work. My mean position curve would look like this. It would go up to 0.3. It would go down to negative 0.3. It'd be sine, so it would be 0.625, 1.25, 1.8. Oh, I don't know what that is. So it's 1.25 plus 0.625. I don't know if that's right. I need to check. 1.25 divided by 2 should be 6.25. Yes, so yeah, it was right. So then that, that plus a 1.25 will be 1.875, and then finally 2.5. So this will be sine. It'll start here, it'll go there, it'll go there, it'll go there, and it'll go there. So what we have is an equation that will take Milton from the bottom of the pool up 0.3 meters to its tallest, back down to the bottom of the pool, smack him through the concrete floor. This is the pool bottom. Going to smack him through the pool bottom and bring him back up to this height. And that just doesn't make any sense at all. We know that good old Milton is moved way up here somewhere. We know that there's been a vertical shift of 1.8 meters, meaning that the lowest we're going to go is 1.5 and the highest we're going to go is 2.1. Okay? And that curve, if we were to put that in, would be this. So there we would have Milton. At least he's not smacking into the bottom of the pool anymore. And we take this equation and we add to it the plus 1.8 vertical shift. So that gets him out from smacking through the bottom of the pool. Now the next problem is we were told that Milton starts at a trough. That ain't no trough. That's halfway through a wavelength. If I want to start him at a trough, I need to move this curve, or one of my options is to move this curve that way. So if I take this and if I apply a horizontal shift to it, so it becomes 0.3 sine 144 t and a shift to the right, so it's negative, of 0.625 plus 1.8 is my vertical shift. I now have an equation that fits good old Milton. He's starting at a minimum, he moves up to a maximum in 1.25 seconds. His period is going to be 2.5 seconds, and his amplitude takes him up 0.3 and down 0.3 from 1.8. Everything's great. We had another choice. You could have moved Milton's curve this way. This would also work. Movement to the right, 0.625, another 0.625, another oh, hold on, how far would I have to move it? A 6.25, a 6.25, and another 6.25. So I'd be moving it 1.875 plus 1.8. So I would take this curve and shift it that way so that my minimum was now matching up where I was starting, sorry, here, and that would be my trough for good old Milton. And lastly, but not leastly, perhaps I had used cosine. Everything stays the same. We get our mean position curve. Goes up to 0.3, goes down to negative 0.3. The period is still the same, 0.625, 1.25, 1.875, 2.5. It's cosine this time, so it goes from here to here to here to here to here. But notice, we're bashing through the bottom of the pool again. What have we forgotten? We've forgotten that vertical shift up. So that vertical shift up goes up 1.8 meters. So my vertical shift is 1.8. Then what's going to happen is I'm going to go up to 2.1 to 1.5, and it's going to look like this. But this has good old Milton starting at a crest. Good old Milton doesn't start at a crest. Good old Milton starts at a trough. Good old Milton starts at a trough and he goes up to a crest. This is what Milton actually does. Oh my goodness, poor Milton. So how can I turn this green curve into that blue curve? With a negative. A simple little reflection will do the trick. So my final answer could be y equals negative 0.3 cosine 144t plus 1.8. That is a good answer. That is a good answer. That is a good answer. And there's other answers. I could have shifted this instead of doing a reflection, but I'm tired of coming up with different answers. Ladies and gentlemen, I hope you enjoyed Milton. We had a good time at the water park. We'll see you on test day.